So the structure of the models would be, this is the classical model I'll start with, and you have looked at the classical models, right? So what are the components of a classical model? Trend, seasonality, something else? Cyclical component and some irregular component. Okay, I'll just take three of them. Okay, so this is trend, this is seasonality, and this is the irregular component. Because the what is the cyclical component? I think, do I have it in the next slide? Yes, I'll come back to that one. Okay, trend is a smooth long-term movement, like the one I showed you here. Okay, smooth long-term movement. Seasonality is a cyclical movement with period less than a year. Okay, so seasonality, mind you, in a series there can be more than one seasonality. Okay, for example, if I have daily data, okay, you can have monthly seasonality. Okay, you can have weekly seasonality. You can have daily seasonality also. For example, if you look at on a roadside, okay, you are looking at the pollution levels, and you are looking at the pollution levels every day for the last 5 years. What did you observe? Any guess? Firstly, a weekly effect. 5 days of the week, you have heavy traffic generally, and the pollution levels would be high. Saturdays it would be much less, Sundays almost negligible. Again, the same pattern follows from Monday, etc. So over the weeks you have high for the first 5 days, it goes down to on Saturday and even lower on Sunday. This happens every week. Okay. Again, you will see a monthly seasonal pattern. Usually in the winter, because of the smog, etc., the pollution level is higher. So if you look at month-wise, also you'll see that there would be a seasonal pattern. Okay, so it need not be. Very often we look at seasonality as just being over months or maybe over quarters. It can be daily data even, over days. Okay, if you look at, for instance, you go to a BPO, okay, and they're taking in the calls, okay, and you'll see that there is a pattern in this, because most people would be, if you want to call your bank, when are you going to call most? During office hours mostly. When you are going out to work, in the evening you wouldn't really bother too much until you have some pressing problems, and middle of the night there would be no calls. So there would be a pattern in this, number of calls coming in. So even over the hours, you can see a pattern. In the 24 hours, there will be a pattern in this. So this is seasonal pattern. Okay, season doesn't only mean the geographical seasons we talk about. It can be on daily data as well. Okay, cyclical movements generally again there would be some business cycles. That's where they started with. It has a period greater than 1. So you can look at it from a economic point of view. You have every 7, 8, 10 years, there is a period of recession, and then you have inflation, etc. So there will be a cycle like that, inflations and recessions, etc. But I didn't keep this separately because very often you can bring this in the trend as well. You don't need to have a linear trend. Okay? So if you have a nonlinear trend, part of the cyclical movement would be absorbed by the trend component, and part of what it remains would possibly go into this component YT here. I'll talk about YT. I'm just, for the time being, assume it's the irregular component as you have been told, but okay. So we have XT broken up into 3 components. TT is the trend, this is the seasonal component, and whatever left is, you see, if I take out TT and ST, what remains would be more or less stationary. Okay, so I'll come back to YT. For the time being, assume it's the irregular component. So we can have an additive model. Okay, so this is a sum of these 3, or we can have a multiplicative model where it's a product of the 3, depends. very often in time series we look at the log of the series, which basically on the multiplicative model, if we take the log, it gives us the additive series in terms of the log. Okay. So the interpretations would be slightly different when you do this, otherwise you can choose any one of the two models. Okay. Again, the first part, as I said, so did I write it here? No, I didn't. Maybe no. Okay. So xt basically is broken up into this. This is the evolutionary part, and this would be the stationary part. That is how I break it up now. And the evolutionary part ET is trend and seasonality. Trend is the long-term, etc. movement, and seasonality is the cyclical movement with period less than 1 year. Okay. So it can be increasing with time. Let's look at trend. It can be increasing. It can be a decreasing series. It can be constant over time, and this is not of much interest though. And there are several methods by which you can estimate trends. You know these methods? Mathematical curve fitting and moving average method. Okay, but I'll just very quickly go through with this. So this is what a trend would look like, something I have drawn here over the years. This is the US population in millions at 10-year intervals. Indian population, if you look at it, it will be a steeper curve. Okay, but that's how you, what you do is basically, why would you want to study this? Lots of policy making problems, right? How many jobs to create in 2025? You have to decide right now, okay? And things like that. So you have to predict this. So beyond this, you'll have to find out, once you have modeled this, you have to predict on the basis of this, okay? Method of curve fitting, this is the first method that we use. We assume that this is a linear function, or maybe a quadratic function, or maybe we assume that the trend is a polynomial. Don't take too large a polynomial, okay, because
we have to estimate many more variables.
Yes, you have to estimate many more coefficients here, these parameters here, but the problem with, okay, I'll ask you a question here. It happens with something like this. I have t xt suppose I have this 8 points here, okay, and or maybe I'll just put it slightly differently, maybe 1 2 3 4, something like this, okay. So what sort of a curve would you take? Would you take a linear model, quadratic model? What do you, quadratic? Okay, why? Oh, you want the best fit, right? And which polynomial should you take for a best fit? Which one?
N minus 1
Yes?
N minus polynomial of degree n minus 1 on the best fit.
Those 10 points? And a 9 degree polynomial? Fine. And what would that do? Okay, you have a curve like this. Right. And then where do you go from this next point? How do you predict? It will go this way, it will go this way, it will go this way. You never know, right? The problem is, and it actually defeats the whole purpose. It looks very nice. It looks very nice if you have a very big model, etc. But whenever you model, remember something that we'll come back to this. Parsimony is one thing that we should be, because firstly you have to interpret the model. Okay? If I take a quadratic, I know where it's going. Okay, I'm sorry it went out through this. Okay, it should have been going through the points. But if you take a quadratic, it should know, you will know where it's going. Okay? It might not give you an exact fit, but then if you take a higher degree polynomial, you get a better fit. But then the interpretation becomes much more difficult, prediction becomes much more difficult, etc. Okay? So you have to make a judicious choice depending on the nature of the curve as to what should be the degree of the polynomial that you choose here. Okay? It need not be a polynomial, it could be a curve like this or exponential curves, etc. And then you use the usual least square method to fit in the curve so that you can find your A, B1, B2, etc. So you minimize this, the error, okay, and you actually get the trend value. So once we do this, once I know my A, B1, Bm, I know my Tt, etc. because given a time point I can get my Tt, and therefore I know what the trend value is at a given time point. I can go beyond the given time points and predict the trend depending on this model here. Okay. So that's the first, this one way. The other way is a very common method, which is referred to as the moving average method. And what is the moving average method? Any idea? Again, it's basically, okay, I've written this down for you. Okay, it's taking a, so if I'm looking at the time point t, I'm taking average or the weighted average of points around xt. So some points before xt, some points after this, okay? And of course the xt points. So take different weights for this and take a linear combination of this to give this tt, okay? The simple moving average, and the one that you have been using probably would be this one, where you take the average of, say, 2m plus 1 point, this is the midpoint, m on this side, m on this side, okay, and you take the average divided by 2m plus 1, and that's the value at xt. So what does it do actually? Why do you do this? So what about xt plus 1? What about t plus 1? You just move from this point to the next. You exclude this point, you add on the next point, because now the center is moved to this. You take m points before this, m points after this, and you go on doing this. Okay? Why is this important, and how does it help actually? How does it really help? It's something like this. And when do you use this? You generally use it. You have, suppose you see that you have observations, there is an increasing trend, and suppose I'm taking a very particular case. The first value is here, the second value is here, up here, the third value is somewhat lower, the fourth value goes even lower, the fifth value goes up here, sixth value is here, seventh value is here, and this is going up again. Something like this, a pattern like this. Okay? So what I have, I'll say this is a low value, this is a high value, this is somewhere in the middle. Then you have a low value again, a high value, a middle value here again. Okay? You have something like this. In this case, you have a pattern, right? And this generally is, you would not get such a nice data, okay, generally. But in this case, you have a period, we say a period of about 3. Okay, so every 3 observations you come back to L, or 3 observations you come back to H, etc. What we are doing is, we are taking the average of these 3 values, okay? And for this point, we take the average and it comes out somewhere here, because it's going to be lower than this, higher than this, and somewhere here, okay? Average of a low value, of a high value, and of a intermediate value, okay? Next point, when you go for this one here, you leave this point out. Okay, so now you are taking the average of this, this, and this. It's an average of a low value, a high value, and a medium value. Okay, next one you leave this out. Again you have a low value, a high value, a medium value. So you see you have the same type of values, same set of values, except it's changing. And what would if you average over this, what happens? This high, low, and medium is going to be averaged out. what is left is basically the trend. Okay, so that's how you actually get the trend. You are basically averaging out over the same types of observations. As you move along, it's the same pattern that you are looking at. Maybe in this case, this comes first, this comes second, this comes third in the next set, but you have the same set. So if this lower is higher than this, then probably, then this is obviously the mean is going to go higher than this. And then you get the, if you join this, you get the pattern for this. Okay, so that's how you use the moving average method to erase out the fluctuations and get the smooth curve through this. Okay, so that's another way of looking at trend. Okay, the point is that you have to identify what the order is going to be like for this, what M is going to be like, and then you can do this. Okay. Now detrending. Now detrending is removing the trend from the model. And how do you do it? The simple way is, this is the detrended series, xt, you have got your trend, you have estimated the trend, take out the trend. I am looking at the additive model. So xt minus tt would be the detrended series. So what remains in a detrended series? The other two components. If you have a seasonal component, it's still there. If you have the irregular values are also there. So this irregular component and the seasonal component, these are what are left when you have a detrended series. Okay. This is from the classical model, this is how you do it. There is, Box-Jenkins actually used a different method. I'll come back to this later, but since I'm discussing trend, I'll talk about this. This is not a way of finding trend, it's rather a way of eliminating trend. Suppose I have values like this. Okay, I'll put these values here. I'll take again a very simple case. 4 here, 8 here, maybe 12 here, maybe 17 here, okay, 21 here, okay. I have a trend, right? It's increasing. What if I take the difference of xt? xt minus 1. How would it look like if I plot this? This minus this is how much? This minus this? I'll plot this. I'll call this is generally referred to as this. So I'll call it delta xt. How would this look like? What would be the first value? 8 minus 4 is 4. Fine. 12 minus 8 is 4. This is 5, slightly higher. This is 4 again. So do you think there is an increasing trend anymore? Is the mean level same now? Okay, so now the mean level has, so very often this trend can be eliminated by what is referred to as differencing. Sometimes one differencing doesn't do it. Suppose you take more than one, so you can do a second difference, etc. But what it does basically, you know from your numerical analysis things, like if you take differences, basically you can reduce it to a constant ultimately. Okay, so that's how you basically can reduce the trend and get to a detrended series. The problem with this method, this is usually, I'll come back to this as I said in the Box-Jenkins model. The only problem with this method is that you do not know what the trend is like. Okay, you don't identify the TT, you just eliminate it. There are two ways. One is, in this case you have identified TT and then taken it out. In this case you do it without identifying what TT is, but very often TT is also of interest. So if TT is of interest, you model TT and then take it out. If you just want to fit in a model without looking at the trend, just in that case, of course, you can use the differencing technique here. Okay, and you take the second difference. If the first difference doesn't work, then you look at the second difference, etc. But we'll look at this. So the differencing can be another way of removing trend. Seasonal component. Okay, it's a cyclical component, periodic movement with period less than 1 year. As I said, now methods of estimating seasonal component is. Yeah. Have you done any methods? You know how to get seasonal components? I just refresh in that case. Okay, in most of the books they'll say ratio to trend methods and ratio to moving average if you are using the multiplicative model. Okay, what we are doing here is we are using the additive model, so I'll call it difference to trend. What it means is that, I'll just go back to the previous slide. I have the original values minus trend, and then I come back to the seasonal with some irregular components in this. So it's the difference between the original value and the trend that I am looking at. So at the first step you eliminate the trend value from the xt series. So xt minus trend, difference to trend basically is if you are doing a mathematical curve fitting, they call it difference to trend. If you are using the moving average to find trend, then they call it the difference to moving average. Okay, it's just the way you have found trend. Okay, now once you get the series, you get something like this. So you get a pattern here. There's an increasing pattern here, but the point is there is some trend here, of course, but you can eliminate that. And you can see that there is the sales data would generally show that there is some pattern in this. Okay? And we want to find out this pattern. So we take this, for each season, mind you, we give a single seasonal value. So we say that in January, the sales are 20% lower than in December, because December, lots of people for the New Year and the Christmas shopping, etc. Again, in Calcutta, in the months of September or October, the sales would be high, etc. Okay, so there would be different seasonal patterns, and we generally make a comparison for this over the different. So we don't look at different seasonal patterns for different years. Okay, so if you're looking at pollution data, so you say that Sunday is 20% as polluted as on a weekday. Whichever Sunday you are talking about. You don't talk about Sunday of this month, etc. That's a different issue altogether. Okay? So you just say Sunday has a 20% value of the original values, etc. So over the months you have the same, over the years you have the same ST value. If I'm looking at monthly data, for instance, so for the last year you have the same value, etc. So all these are going to be equal. And what you do is, you have fitted in a trend. Now if you have, say, 12 years data, okay, and you have the original data, you have the trend values, monthly data, 12, or maybe I'll take 10 years, it will be easier, okay. 10 years monthly data. How many observations do you have? 120 observations. Okay, each year you have 12 observations for the 12 months. For 10 years you have 120 observations. Okay, how many January data do you have? 10 January data. Okay, this 10 January data, these are the seasonal values, because you are taking the difference. You take the observations, you fit in the trend, observation minus trend, you have got 10 detrended values for January. Okay, should they be equal? Should be, because I have taken the trend out, so what remains is the seasonal value. Okay, generally they would not be equal, there would be some fluctuations. Okay, so what you do is we average out this. So over the 10 years, I am fixing up January, I have got 10 values for January. What I take as the seasonal component for January is the average of these values here. Okay, so over the different years you take the average and you get the January. Similarly for February you have 10 observations, you average it out and get the seasonal value for February. Okay, and this generally should be adjust the averages, so the sum of all the seasonal averages is 0, This gives us seasonal effects ST. Okay, so you make an adjustment, or maybe sometimes you put it in percentages so that you know that this is 20%, this is, you get a value of 120, you know that it's above the general level. You get a value of 90, you know it's lower than the 100% level. 100% is the base in that case. So you make some sort of an adjustment and you get the seasonal values for the different months. That's a seasonal component. Okay. And then what you do is we deseasonalize the series. Okay. How do you deseasonalize it? Just subtract the seasonal value from the detrended value, or maybe you can take it as xt minus, you have estimated tt, you know your t values, you know your seasonal values, so you take this 2 out and you only are left with the irregular component here. Okay. So this yt basically is the deseasonalized detrended series. Okay. You have taken out both the trend and the seasonality. Okay, as I said, you can remove trend by differencing. Can you remove seasonality by differencing? Yes, if I subtract last year's January value from this year's January value, what happens? The January effect goes. Similarly, if I take the difference between the February values, okay, once you take the, do you agree with this? Okay, so if I difference over the whole period, okay, this year's January with last year's January, this year's February with last year's February, what happens? What remains? Suppose I hadn't taken out trend, what would have remained? The trend value. Okay, but there would have been no seasonal fluctuation in the dxt. Agreed on this? Okay, so another way is to, instead of doing this, if the seasonality is of period h is 12 for monthly data, weekly data is 7, you take a difference of 7th order difference rather than you take delta xt minus delta xt minus h. Okay. So this year's value from last year's January value, February value, or if you are looking at weekly values, Monday minus last Monday, Tuesday minus last Tuesday, etc., and you get rid of the seasonal values. But again, if you do this directly, you can get rid of seasonality, but you would not know what the specific seasonal values are. So the classical method actually helps you to identify the seasonal values. Okay. In this case, you can eliminate seasonality without even identifying what the different seasonal values are. Okay. So differencing can help you remove trend and seasonality, but without identifying them. The classical models, you can find out trend, you can find out seasonality, and then remove them from the original series here xt to get the irregular component. Okay. Any questions up to this point? Okay, no. Okay, one way of smoothing data, maybe maybe I'll come to this slides later. For the time being, I'll just skip this, okay, because, okay, let us look at a detrended deseasonalized series. Often looks irregular, okay. Mind you, this is mean stationary because I've taken out the main two components which affects the mean, and therefore this is a mean stationary series. But then yt often has a pattern of its own. The question is, can we capture, this is not exactly irregular. Okay, the first figure I had drawn here, the craggy figure there, can we find a pattern in this? There is no increasing trend or there is no seasonality, but still there can be a pattern in this data. Okay. For example, if you look at, I started with this, if you look at an ECG for instance, okay, what sort of a series would you think? ECG, a doctor looks at it, it's not a straight line, right? What happens if it's a straight line? Okay, So you don't really need to analyze it anymore. Okay, if it's a straight line, it's fine, it's done. Okay. What happens if you have a trend in the ECG data? An increasing trend, or maybe a decreasing trend? Again, then you don't need to look very long. Okay, if you have a trend in the data, right? So basically there will be no trend or seasonality, okay? But still there is something in the data or in this pattern, there would be some sort of a pattern that would be interested in. It's not flat. Okay, the movements, the doctor actually looks at these movements, okay, he doesn't do a time series analysis, he does it from experience maybe, but there should be some pattern that he actually identifies whether this is a normal person or is he a sick person. Okay, does he have a problem? So there should be some underlying pattern that he actually from experience looks into. So very often, even if you don't have a trend or a seasonality, okay, and even the curve would not be flat, and there would be some modulations in the curve, and there may be some hidden patterns in this which we might be interested in. Okay, so that's where we come to the pattern of this YTs, and that's where Box-Jenkins models came into being. Okay, and before I come to the Box-Jenkins model, what they did was they had this 3 keywords here: identification, a choice to be made regarding the type of model, estimation once you have made the model, but the problem was that there was no fixed one model that you can be said to be the best. Okay? You had alternative models, and therefore you go for a diagnostic checking to check whether the estimated model adequately fits the data. Okay? So this step, and if it doesn't fit the model adequately or the data adequately, you go back and re-identify a new model and go through the whole process again. Okay? You keep doing this until you get a good model. Okay? Okay. Now let's come to the basic definition of stationarity. Usually I will be assuming expectation of YT is beauty, and this is the covariance between YT and YT plus H. It's referred to as the autocorrelation. We call it the autocorrelation function of order H. That is, you are looking at, so it's something like, if I'm looking at weekly data, I'm looking at the correlation between the Monday pollution level and the Tuesday pollution level. Tuesday with Wednesday, Wednesday with Thursday. This is the correlation of first order. Okay, that's H equal to 1. Okay. If I look at Monday with Wednesday, Tuesday with Thursday, Wednesday with Friday, and so on and so forth, I have a autocorrelation of order 2. H is equal to 2 in that case. Okay, so you're looking at autocorrelation because you're looking at the correlation between observations in the same series. It's the same variable that or same series of observation that you are looking at, and this is gamma TH, and gamma T naught would be the special case when H is equal to 0, and this becomes the variance. Okay, and very often ACF, this stands for autocovariance function. You can have a autocorrelation function also, where you divide gamma TH by gamma T naught, and you get, of course you can't do it here, maybe for the next step I'll tell you why you can't do it here, and you get to the autocorrelation function. Okay. Now YT is stationary if this mu is independent of T. That means the mean does not keep changing like this. The mean level is the same whatever the T value is. So YT is a sort of a flat series. There would be ups and downs, but this is a flat series. And the second thing is that this gamma T also, this covariances between T and T plus H, they would depend on the difference between these two values here, but not on which point it is. So it's independent of T again. It can depend on H. Okay, if it's constant for H, it's It's generally not constant for age, so it will be, what would happen generally? How would it change with age generally? Remember what H is? H is the difference, right? So how do you expect the autocorrelation to change with H? What does, if it's constant, what does it mean? Yes?
No change. There is no change if it's constant.
Okay, there is no change. How do you interpret this?
Whatever distance we take, the association of relationship is constant.
Is constant. Okay, so is it a feasible way of doing it? No. What happens is that two observations would be more related if they are close to each other. Today depends on what I did yesterday, not what I did, say, 100 days back. Okay, so generally as age increases, this would be decreasing. The relationship would be less and less as the difference between the observations increases. So in general, as age increases, and this happens in most series, okay, this would be going down. But the more important thing is that Monday and Tuesday's relationship, or Tuesdays and Wednesdays relationship, this doesn't, it will be the same. Okay, that doesn't depend on T. Whether you are taking Monday or Tuesday or Thursday, it doesn't matter. So it's independent of T, and that's how you define stationarity. This is basically the weak stationarity. Okay, so how to choose the best model? You consider what is referred as autocorrelation function and leads to what is referred as a correlogram, the partial autocorrelation function of the PSCF. And these days, mostly you ask for the archaic acid formation. In fact, if you fit in a model using some computer program, they always give you the AIC value also, okay? And I'll tell you how to use this value. But before that, okay, I think I start on this. Maybe I'll just go back here. So what would be the parameters that we have? We have mu and this gamma h. How do you estimate mu generally? This is flat. Just take the sample mean. So I haven't talked about it here. So it's basically you use it by the sample mean because there is no change in the mean. So over all the observations come from the same or have the same mean, and therefore you can take the sample average as an estimate for mu. Okay. I'll ask you a question here now. I'll go back to the very first example I talked about. Okay. I talked about looking at heights of growing children. One single child, and you're looking at the heights of this, okay, over 20 years. Okay. At what stage are we now? Can you relate it to this problem here? Would you have taken a mean of heights there? Okay, I'll go back and okay, it's something like I am looking at a particular child. Height at 0 LBD, 1 LBD, okay, and 20 LBD. I have this, so maybe I'll take x1, x2, x20. These are the heights of a child. Okay. Would you take the mean of this? What would that stand for? If I take the average of this, does it mean anything? No. So we can't take the average of this. Why?
Because these are dependent variables. There's a trend.
because there is a trend and they come from different, because this child had, okay, average of, came from a population with average of 1 feet, this from 1.5 feet, etc. And by this time it's maybe 5 and 3/4 feet, etc., something like this. Okay, so no point taking an average of this. Okay, but I find the trend, and this is a trend. Okay, so if you are taking out the irregular movement, you find the trend. Suppose this comes very close to this, and then what I'm doing is I'm taking the difference here. What happens to this series now? What about this series? What about the mean for this series? They will be similar, because what would happen basically, if the child is usually short, okay, shorter than the average, then all these values is going to be negative, but they would be close to 0. Agreed on that? If it's 2 inches shorter, then these values are going to be 2 inches everywhere. Okay? So once you have taken this out, you are coming back to the same mean level. Now I can take the mean of this to get the mean of the difference series. Mind you, I have differenced it out. I have taken the trend out. I am taking this trend out. Now this is a flat series. Now this series would more or less look like values are somewhere here. Okay, depending, at some years he may be above average, some years he may be less than average, etc. And you can get, it might not, this can be 0, the mean level, it can be at some other mean level as well. Okay, so you can take the average for this as an estimate for the mean. This mean now is time independent. Okay, as for this, as for gamma h, you take the sample autocovariance function here. This is yt minus y bar. Mind you, again, y bar is a estimator for mu, so it's same, it's independent of time. So yt minus y bar, yt plus h minus y bar, that gives you the autocovariance function. And if you have a stationary process, the variance do not change over time, and therefore it has the same variance. Both yt and yt plus h has the same variance, and therefore the autocorrelation function would be given by this divided by gamma hat 0. Okay, so this is a sample autocorrelation. This is the autocorrelation function for the parent series. This is for the population, and this is basically the sample autocorrelation function. And a plot of rho h or RH against h is referred to as a coelogram. We'll come to this coelogram later on, but this plot generally is referred to as a coelogram. Okay, we have something called the partial autocorrelation function, gamma h. This is the autocorrelation between yt and yt plus h, eliminating the effects of the intermediate observations. Okay, this is a little bit more difficult to do, but okay, these days the computer programmed with this. You need to understand what basically this gives you. It's something, what is the difference between simple correlation and partial correlation? Normal, in your statistics classes you have done it, right? What is the difference? When do you look at simple correlation and when do you look at partial correlations?
Partial is conditioned one.
Conditions in the sense? Okay.
That is with respect to some another variable, 2 variables.
You have 2 variables, x and y. When would you do a
Correlation is linear correlation.
Okay.
Only for 2 variables.
Okay.
And in partial correlation, we fix some another variable other than these 2.
You have other variables. Suppose I have 3 variables, x, y and z. When you do what is a simple correlation and what would be a partial correlation in that case?
Simple correlation will be between x1, x2, x3.
I have just x, y, z, 3 variables. When would you What would be a simple correlation? What would be a partial correlation? Okay, that would be simple correlation. Okay, and what would be partial correlation?
Eliminating the effect of.
Actually eliminating the effect of it. What happens is, suppose I look at x and y and just don't bother about what z is. Okay, what happens is x and y may be correlated because, not because they are themselves related to each other, but because they are both related to z. Okay, I'll give you an example, and this is time series data. You have lots of examples here. Okay, you try this out. Okay, go back and take the population size, Indian population, from 1990 to 2015. Okay, and look at the amount of steel produced over this period. Okay, 1990 to 2015. Write down both the series and do a correlation. What did you expect? Highly positive correlation. Why? I'll put it slightly different. Forget about population. One, you have the steel production and the number of babies born.
In first example, there is an impact of some economic development and industrial development.
Okay, number of babies born I have got, okay, and the number of, and the amount of steel production. And you get a very high correlation between these two. And how do you explain this?
Number of people are more, so they will use more steel.
Number of babies born depends on, what depends on what? Number of babies born depends on the steel production. Yes?
Must be some confounding variable.
Yes, if you do a simple correlation, and I can assure you, if you do this, you will find a very high positive correlation. This is simply because both are increasing with time. So if you take the time factor out, there will be no correlation between these two. There is a third variable which actually relates this to, and very often in time series we have, if you have two increasing trends completely unrelated, okay, just because both are increasing with time, what would happen? They would get related to each other. Okay, so in that case, obviously you need to eliminate the time effect. Then we use the partial correlation, where we look at the two series eliminating the effect of time from each of the series. Okay, so similarly, when we look at yt and yt plus h, these two might be too far apart and they might not be related. They are related because of the intervening period. Yt is related to yt plus 1, etc., because this depends on this depends on yt plus 2 depends on this. And because there is interdependence among these variables, these two becomes related because of the effect of these variables here. So what happens if I take this out? If I take this out, probably it will show that these two variables are no longer dependent. So previously what we did was, we didn't take this out. That's the simple correlation, the original autocorrelation function. And the partial autocorrelation function would be doing the same thing, but now you eliminate the effects of the intermediate values. So both the SCF and this is referred to as the PSCF, play a major role in identifying the series that comes up, okay, the Box-Jenkins models. Okay, so just these are basically the difference in the two definitions. Okay, and how to know whether RHs are different from 0? So test for significance. RH are generally normal with mean 0 and 1 by n. This can be proved. Okay, and therefore, if it's a normal distribution, 1.96 is basically the
95%.
Okay, 95% confidence intervals would be based on this, and this would be the variance. Variance would be, or the standard deviation would be the reciprocal of this, n to the power half, And if the RHS lies outside these limits, then you know that they are significant. If they are within these limits, you know that the RH value is insignificantly different from 0. So you can take them. What do you mean by insignificantly different from 0? You can as well take them as 0. Okay, that means you obviously RH should not be exactly rho h. Rho h is the actual values. You don't see the actual values. You're looking at a sample. So RH should differ from rho h, but you allow it to differ by this amount. Okay, and if it's less than this, you know that the rho h value is going to be 0. Okay, so you have these two lines and check when RH goes beyond the lines, and when it goes between these lines, you know that they become insignificant. Okay, this is how it looks like. These two series I had taken, and this is the SEF, and this would be the PSEF. You get the important part here is that, can you see it from the back, because this is not coming out very clearly. Maybe for this one you can see the two blue lines here. Can you see these two lines here? Okay, there are two lines here. These are a little bit, I don't know, for some reason this is one line here, one line here. This basically are the 1.96 root over n lines, okay, plus minus. Okay, so you can see that these 2 points of the ACF are, or these 3 points are above this. Everything else goes below this. What does that mean? What does that mean? These 3 points are above the blue line. This first, second, third. First is at 0, second is at 1, third is at 2. What would that mean?
First order differencing is out of bound.
It means that first one is rho naught, okay, so we didn't bother too much about this. Second one is the rho 1. What is rho 1? Is the autocorrelation between today's value and the next day's values, consecutive values. These are positively related. What about rho 2? Today and day after tomorrow. These again are related. But what we can say is beyond that it goes below the line. It means that it becomes 0. So rho 3 is 0, rho 4 is 0, which means that after 2 days there is no more effect. So whatever effect you have for a particular day, basically it's for 2 days only. Beyond that the effect does not stay. It's like putting on a perfume. For the first hour, for the second hour the perfume stays. After that you don't have any effect. How does it help us? You see, I was trying to model, if you remember at the very onset when I talked about time domain, I said xt is related to its past value, xt minus 1, xt minus, how far do I go? In this case we'll go 2 steps only, because beyond that there would be no relationship. That's how you identify models, okay. So you know that beyond 2 steps, xt minus 3 would not have any effect on this, or xt minus 4 will not have any effect of it. So that helps us to identify the models. Similarly the PSF, in this case this PSF only is, everything else is beyond this. Maybe there is something here which is about 12, which really means that there may be a seasonal effect here. Okay, so this is how you read this, and maybe I'll tell you why this is important. Should we take a break now, or okay? Okay, before I start this, because it will take a little time. Okay, we can break for tea and maybe any questions before the break? Yes?
Previous like
Okay.
SEF plot, how will interpret that? Again, that is crossing the bound.
This one. This is